Hello, friends. Welcome. We shall continue our discussion. Today, we shall start with the induction motor drive. There, I will take the three-phase induction motor drive. To start with, this three-phase induction drive makes use of the three-phase induction motor. We already know the definition of drive, electric drive, and in that the motor used is electric motor and it is induction motor, it is three-phase induction motor. That's how we can define three-phase induction motor drive. It is an electric drive employing three-phase induction motor. Now, the motor used here is three-phase, and this drive is very important. That part let us make clear in the beginning. Very important drive. From the applications point of view, of late we find this being extensively employed, be it industrial or elsewhere also. The total number is increasing, three-phase induction motor drive. And the motor we are using there, the three-phase motor, the reason for this nowadays the drive being default induction motor drive is the induction motor itself. The three-phase induction motor, as we all know, is the rugged motor, very strong, physically, mechanically very strong, rugged motor. That's why this motor is used extensively, to such an extent that this is called industrial workhorse. Industrial workhorse. The induction motor is called industrial workhorse. It is used extensively. The reason for that mainly is it is rugged. Now, why it is rugged induction motor? Because we have the usual competitor to it, which is that DC motor. So as compared to DC motor, induction motor is very rugged, very strong mechanically. What is the reason? Yeah, anybody? What is the reason why it is mechanically so strong? It is like you start and then run it. It keeps running for hours and days together continuously. Doesn't require maintenance, as in the case of DC motors. What is the reason for that? The reason is here there is no brush type of arrangement, whereas in the case of DC motor we have the brushes present. The moment the brushes are there will be sparking problem, there will be wear out of the brushes, there will be deposition of carbon. All this requires constant maintenance, and that brings down the reliability as well as the life. The overall maintenance cost will be more. This is not there in the case of induction motor. That's why they are very strong, they are very rugged. And one disadvantage was there with induction motor, and that was the advantage of DC motor, and it was the ease of control and the accuracy. DC motor controlling is very easy, and then it can be controlled very accurately. Main reason is in the case of DC motor, you can control the armature independently and you can control the field independently. You have the access to armature, you have the access to the field. Nothing but you have the access to the armature current, you have the access to the flux. It is, you can control the flux independently, you can control the armature current independently. And in the case of induction motor, it was not there, because if we try to control changing the supply voltage, then the flux as well as the current both will get changed. We do not have access, we didn't have access to these things independently. But however, nowadays, due to a very interesting concept called as cross vector control, we can control the induction motor in a similar manner as we control a DC motor. That is why even the control aspect wise also, induction motor is comparable to the DC motor. Because of this better control, in addition to its biggest advantage that it is strong, induction motors are extensively used nowadays. Of course, this control approach, what I mentioned, cross vector control, requires a sophisticated control mechanism involving a processor. However, that is available nowadays. It is thanks to the developments in the digital technology like processing, the DSPs, that this control is becoming possible. Okay, so the three-phase induction motor is the industrial workhorse. The drive employing that is the one which is almost the default drive in most of the applications. Now, quickly, what is this three-phase induction motor? We will try to recap quickly, because with this background, our further discussions will be more meaningful. We all know that in the case of three-phase induction motor, there are two specific important parts. One is stator, another is rotor, and it is the stator to which we give the supply, and the rotor is having a shaft, and to the shaft we connect the load. We get the mechanical output from the rotor side. The electric input given to the stator is converted into mechanical output at the rotor. So the energy is transferred from the stator to rotor. I repeat, energy, power is transferred from stator to rotor, and there is no electric link between stator and rotor. Are you listening carefully? So this three-phase induction motor acts like a transformer, wherein the stator happens to be primary, rotor happens to be secondary, and this being a motor, it rotates. Hence this transformer I can call as rotating transformer. Only thing is, the physical difference is rotary is rotating. The electrical difference is the secondary rotor frequency is different from the stator frequency. If stator frequency is F, rotor frequency is, anybody? Rotor frequency is Fr equal to S into F, where S is the slip. So the three-phase induction motor is rotating transformer, works making use of the principle of electromagnetic induction, wherein the stator is primary, rotary is secondary, no electric contact between the two. Good. Second, this is what I mentioned. The rotor current is set up by means of electromagnetic induction. So this is a motor. The basic principle of motor is what? A current carrying conductor kept in a magnetic field will experience a force. So we require a current carrying conductor, we require a field. So we give supply to the stator, it produces the field, and we require a conductor with current. That means in the rotor conductor I have to set up the current. That current we set up by means of electromagnetic induction. Whereas the same thing the current in the armature conductor is set up by means of physical contact in the case of DC motor. That is why DC motor is called conducting motor, whereas this motor is called induction motor. That DC motor is called conduction motor, this motor is called induction motor. So the I in induction motor, IM induction motor, that induction, it refers to this aspect, the setting up of current in the rotor by means of electromagnetic induction. Next, the rotor starts moving because the current carrying conductor is there, and the stator will have the field, and that field rotates. It is called rotating magnetic field, and rotor starts moving. The speed at which the stator field rotates is called what speed? Synchronous speed. This is called synchronous speed, and normally it is abbreviated as ns, rpm, or omega ms, radians per second. And the rotor speed n, rpm, or omega m, radians per second. And the rotor speed is always less than the synchronous speed. This we know. It's a normal question, very standard question. Why the rotor speed is less than the synchronous speed? Okay. Next. So I mentioned the rotor speed is less than the synchronous speed. N is less than ns. We feel as if the rotor is falling back, rotor is slipping back with respect to rotating stator field. That slipping back, that falling back is represented in terms of a parameter called as slip, abbreviated as S, symbolized as S. Mathematically, it is this ns minus n divided by ns, or omega ms minus omega m divided by omega ms. And with this equation, we can have omega m, or we can have n as ns 1 minus s, omega ms 1 minus s. All this we know. So this slip, ideal values are s equal to 1 when n is 0, s equal to 0 when n is ns. Of course, that 0 will n equal to ns, that question doesn't arise at all, because rotor will not be able to reach the synchronous speed at all. So slip equation is this. With that, the actual speed of the rotor can be obtained like this. Now we will come to very important issue, the equivalent circuit. All of you, please observe this little carefully. We should be able to obtain the equivalent circuit ourselves. What is this equivalent circuit? The electrical circuit representing the induction motor. Same thing we have done with respect to the transformer also, na? The equivalent circuit. In this case, the induction motor that we are considering is 3-phase induction motor. Hence, we represent one phase and take it as the same for the other 2 phases also. That is why normally here we have per phase equivalent circuit. The analysis we do for that circuit, and we extend it for the entire motor. Now, I will show the development of this equivalent circuit quickly, so that we appreciate what is there in that and what level of equivalent circuit we should use. Okay. So to start with, see this. This is something that we know already. Look at this. Okay. So this, I have stator, this is stator, this is rotor. I am giving supply to the stator. The per phase supply is V, let us say. Then stator is having some resistance, some reactance. The stator is drawing a current IS. Then stator to rotor, no connection, air gap is there, and power is transferred by electromagnetic induction. A voltage is induced on the rotor side, and this voltage induced on the rotor side is S times the voltage when it is static. As the rotor starts moving, the amount of voltage changes. It is given as S into E2, and the current in the rotor is IR, and the reactance is XR when it is static, resistance is RR when it is static. When it starts moving, it is S into XR, similar to S into E2 for the voltage. Now interestingly, why this XR when the motor is static becomes S into XR when it is running? Because this X is dependent on F. X is 2 pi FL now. So when it is static, this frequency and this frequency is the same. But when it starts rotating, this frequency becomes S into F, this frequency. That is why this reactance becomes S into the reactance corresponding to standstill. Very important stage. This is to be very clear to us. Stator, rotor, no connection. These parameters, the absolute parameters of the rotor side, RR, XR at standstill, E2 at standstill, S into XR, S into E2 when it runs with a slip S. Good? Okay. So we shall proceed. Next, look at this. Now, I will represent these parameters of the rotor onto the stator. I will represent these with respect to the stator. It's called as referring, and this E2 I will refer to this side, it will become E2 dash. XR I will refer to this side, it will become XR dash. RR I will refer to this side, it will become RR dash. So these values are the referred values to the primary. When we do the referring, what is the basis? All that we know. Okay. So now these values are not absolute values. These are the real values, whereas these are the referred values. Now look at this. What I am doing, I will divide these by S, E2 dash by S, XR dash by S, SS gets cancelled, RR dash by S. So S into E2 dash by S will give me E2 dash, this will give me XR dash, this will give me RR dash by S. So you can see this and this, and what we find is this voltage referred to the primary, this voltage referred to the primary, E2 dash becomes the same as E. That is why when this and this voltage is same, this and this voltage is same, I can as well remove this part. That's what we have done, and we have represented this by the corresponding reactance, and the equivalent circuit becomes like this with the referred values. The per phase voltage is V, stator current is IS, and the current through the magnetizing path is IM, and current through this path, this is actually referred rotor path, is IR dash. It is IR here, it is IR dash here, the referred current IR dash here. Now this is the exact equivalent circuit. If to make the circuit I can be okay with approximation, what we can do, we can shift this path from here to this side so that our mathematics becomes easier. That's what we have done. This was actually here, we have shifted, and it results in bit of error but makes the mathematics easier. That's why this is called approximate equivalent circuit. Now still more approximation is this path itself I will neglect, the magnetizing path itself I will neglect. I will get this. Look at this. I will get this. So RS, XS, XR dash, RR dash by S. Very simple circuit now for analysis, no parallel path at all. And next, with that, look at here, IS and IR dash both are becoming same because this is neglected. RS, XS as it is there, XR dash as it is there. Now I will split this RR dash by S as two parts. One is RR dash, another is RR dash into 1 minus S by S. If I add these two, I will get RR dash by S only. Now this is interesting. So what we got here is an equivalent circuit with stator parameters as well as with rotor parameters XR dash and RR dash, with an additional parameter which actually represents the load, So here this RR dash by S actually includes the effect of the rotor resistance as well as the load. Here the load is represented separately. This circuit is an important circuit. Though it is approximate, it gives you the clear idea about the induction motor. Different parameters. Look at all these things. Actual, referred, approximate, still approximate, with load. Are you able to see? Good. We should be able to get these things ourselves. Next, we will move on. If you see that equivalent circuit, I can get the current IR dash as V, the voltage there, divided by the impedance, the resistances, and then the reactances. Very simple, no? It is a circuit analysis. And how much is the power transfer to the rotor? Power transfer to the rotor, if I call it as PZ, it is IR dash square RR dash by S. That is this, the power transfer to the rotor. Is how much is the current here? IR dash. How much is the resistance here? This is the rotor part, na? RR dash by S. IR dash square RR dash by S is the power for one phase. For three phases, 3 times that. That is the power transfer to the rotor. So we shall call it as PZ, power transfer to the rotor, typically called as air gap power. PG equal to 3 times IR dash square RR dash by S. Next, here that is the total power transferred to the rotor. Out of this total power, we have split that RR dash by S as 2 components. The power for this parameter indicates the loss in the winding, the rotor winding. This RR dash is the equivalent resistance of the rotor winding, whereas power here in this parameter represents the power to the load. Actually, it is the mechanical power that is developed. This is the total power given to the rotor, out of which this much we lose as copper loss. The remaining is the power that is converted into, the remaining is the electrical power that is converted into mechanical power. So that step is a very critical step. So rotor copper loss here is IR dash square RR dash for one phase, 3 times that for all the 3 phases. And electrical power converted into mechanical power is nothing but the gross power minus copper loss, and that is PM equal to the mechanical power, the electric power converted into mechanical power, PG minus PCU, which will be this minus this. I actually get this, and here look at this. This is what we got. This is the one which represents the load. That's how we have put in the equivalent circuit now. Good. So now all this PG, total power given to the rotor, copper loss, remaining mechanical power developed. PG is to PCU is to PM, 1 is to S is to 1 minus S, the ratio. This is the normal standard relation that we come across now. Okay. So next, torque developed by the motor. So this torque, we know the equation omega T equal to P na. So for the gross power, torque developed by the motor is torque into the synchronous speed, nothing but torque equal to PG by omega ms, and PG is 3 times IR dash square RR dash by S, PG, and divided by omega ms. We can as well put it as mechanical power developed divided by the actual speed 3 by omega m IR dash square 1 minus S by S. Now, motor output at the shaft. This torque is the torque generated. This power is the mechanical power generated. But the mechanical power or the torque available at the shaft will be less than this, because there will be friction losses, other losses. Hence, the actual output at the shaft will be less, and the torque there at the shaft is obtained by deducting friction, windage and core loss torques from the developed torque. Okay, so next, look at this. We have the torque, and if I take the differential of that and equate it to 0, that is where the torque becomes maximum. We want to know the condition for the torque to become maximum in terms of the slip. So when dt by ds equal to 0, the corresponding slip we will put as Sm. We get the equation like this, wherein the sign can be plus or minus depending on whether the induction machine is operating as a motor or it's operating as a generator, motoring or generating. This is the slip Sm. It is not maximum slip, it is the slip for maximum torque. So substituting this in the expression for torque, we get T max as equal to this. Observe this equation, the maximum torque equation. In this torque equation, we do not have RR at all. That means the maximum torque doesn't depend on the rotor resistance. Maximum torque is independent of that. Of course, the instant when the maximum torque happens depends on RR. The instant at which it happens depends on RR dash. Is it okay? So I repeat, this is the slip, not maximum slip. This is the slip for maximum torque, and the maximum torque expression is this. Okay. So keeping this in mind, using these equations, we can approximately get the torque speed characteristic of the induction motor, and that we already know, very standard omega T characteristics. And this is the torque, this is the slip. It will be like this, wherein this is the starting torque, this is the starting torque, and as we go further here like this, slip will decrease, and this is the maximum torque or the so-called pull-out torque. When that occurs, the corresponding slip is Sm. The corresponding slip is Sm. Is it okay? So normally the operation will take place in this region. That's why this region is called operating region. This region is called operating region. Normally the operation will be at points like this, which is actually the value of slip nearing to zero. The normal operation of the induction motor will be at very low slips, very low slips. At very low slip means the speed nearer to synchronous speed. The slip of the order of 0.04, 0.03, which means 3%, 4%, etc. This is the operating region. And you remember we made a mention about this operating region where where anybody can you recall induction motor? Yeah, when we discussed about stability. So this region is also called a stable region. That's why we operate the induction motor in this region, whereas this region is the unstable region. This region is the unstable region. Okay, so with that much of background regarding the induction motor, next class we will start with different topics. Shall we stop there? Bye.